In this video, we will learn how to model two PSC box girders on either side of a bridge alignment, while following super elevation controlled by their individual top-mid locations. You're currently looking at a cross-sectional view of the alignment, where the alignment line passes through the center, and the girders are placed 20 meters apart, specifically one located at positive 10 meters and the other at negative 10 meters in the y direction relative to the alignment. If you observe closely, the control point for super elevation for both girders is located at the top mid location of their respective sections. In this case, both the path of the PSC box girder and the control point for super elevation coincide at the same point, simplifying the process. In CIM, we'll position the section so that the reference location in CIM and the top midpoint of the section overlap. Now, let's look at the step-by-step workflow to define and model these PSC box girders under such conditions. We'll start from the data ribbon in the worktree. Open the Curve Library mode where our PSC box girder section is already defined. The first step is to open the User Section mode for the PSC box section. Inside this, we'll define a vertex group for the super elevation. Since we earlier mentioned that the reference point location of the section and the control point for super elevation coincide, we'll select Variation by Super Elevation option, and using the cursor cross-selection, we'll pick the vertex node at the top mid-location and assign it as the master vertex. Then, select all remaining vertices of the section as slave nodes. From the menu panel, click Apply to save the vertex group, and then at the top of the modeling window, click Apply again to save and exit User Section mode. Next, using the Path Linked Entity option, we'll assign this section to the default constraint path. Click Assign and Preview, and then at the bottom, click Apply to create the member. Let's now move to Base mode and enter the Assembly Unit mode, where we'll model the parallel PSC box girders. Knowing that they're 10 meters away from the central alignment, we'll create two main constraint paths, one at +10 meters and another at -10 meters in the y direction. From the Path dropdown, select Main Path. Then using the cursor cross-selection, select Constraint Planes and enter an offset distance of +10 meters. Click Add. Next, change the offset distance to -10 meters and click Apply to create both paths. Now, we'll assign the previously created Curve Library to both these paths. Go to Curve Assign Library and select the left path first. On the second tab of the menu panel, under Super Elevation, choose Deformed. The super elevation defined in the layout will be applied to this member only if the deformed option is selected. Set the number of reference points to 1 as the PSC box section has a single control point. Enter the reference point offset distance as 10 meters. This setting instructs the program to place the reference point for super elevation calculation 10 meters away from the default path. As a result, the super elevation reference point aligns with the main constraint path along which the PSC box girder will be assigned. Click Add to assign this to the left path. Repeat the process for the right path. This time, enter -10 meters as the reference offset for super elevation. Click Apply to save the assembly unit. Next, let's create the bridge alignment with the following super elevation values: -5% on the left and +5% on the right. Name the alignment assembly and click Apply to generate it. Now assign the created assembly unit to this alignment. Select the layout, click on Add tab, then click on Preview, and finally Apply. Switch to left side view in the model window to verify how the PSC box girders are positioned with super elevation calculated from their top-mid locations, 10 meters away on either side of the default path. In this case, you can observe that the top midpoint of left girder and right girders remain at the same horizontal level. So this is how you can model the PSC box girders as shown in the initial drawing. To see the effect of zero reference offset distance, create a new assembly repeating earlier steps. Create constraint paths at +10 and -10 meters. Assign the same curve library, but this time, when selecting deformed for super elevation, leave the offset distance as 0 meters. Create another layout, this time shifting the alignment by +50 meters in Y and applying the same super elevation values. Assign the new assembly to this layout. Check in left view and observe that now super elevation calculation is done directly from the bridge alignment path itself, causing both girders to have slopes starting from that origin. In this case, you can observe that the top midpoint of the left girder has shifted downwards, whereas the top midpoint of the right girder has shifted upwards. However, the slope remains continuous from one girder to the other. Finally, there's a third method for defining reference offset distances. While creating main constraint paths, before placing them, look at the bottom of the menu panel where a super elevation section is available. Here, set the reference offset distance as +10 meters for the left path and -10 meters for the right path. Leave calculation point offset as 0 since the control point and section reference coincide. After creating paths, assign the PSC box curve library as before with deformed super elevation. Save the assembly, go to base mode, and create a new layout starting from -50 meters in Y. Apply the same super elevation configuration. After assigning the assembly units and checking the left view in the model window, you'll notice that the super elevation results from Method 1 and Method 3 match perfectly. Both PSC box girders align with their intended super elevation control points. The core difference lies in how the reference point offset distance for super elevation is configured. In Method 1, you manually assign the reference offset each time you add a curve library to a constraint path. This gives flexibility, but requires extra input during each library assignment. In Method 3, you assign the reference point offset at the time of creating the constraint path itself. This allows any subsequent curve library with a super elevation group to inherit this offset automatically, saving time and reducing the chances of manual input errors. Additionally, if your design doesn't need any super elevation offset and should strictly calculate slope from the default path, Then use Method 2, where both paths are created without offset distances. Both Method 1 and 3 achieve the same physical outcome, but differ in operational convenience. For complex projects with multiple curve libraries assigned to the same path, Method 3 is typically more efficient. That's how we can successfully model two parallel PSC box girders with individual super elevation control points.